Good evening, everyone. So today is the last class. After that, I will take one uh, revision class. That will be the last class. So in this class, first I will uh, uh, revise the SDP semi-definite problem. Uh, then solve some problems, questions. Okay. So then I'll conclude the class. So let's start now. So the SDP problem is that let us take a linear program problem. So minimizing. So the optimization problem. Let us take the optimization problem like that. C transpose X subject to AX equal to B, and this is a linear constant. Then so this is the equality constant. So then one inequality constant is that this x1 f1. So f1 is a matrix. So x1 f1 plus x2 f2 plus xn fn plus one another matrix G all together is greater than equal to 0. So this greater than equal to is means that positive semi-definite. Okay, so that means summation of xi equal to 1 to n fi plus g greater than equals to 0. So this is the constant. Okay, so this is the linearly weighted combinations of matrices. So now, how to solve the SDP problem? So there will be some SDP relaxation so that we can reduce the complexity of to solve the problem, optimization problem. So here one example is that SDP problem for SDP for detector. So the objective function is that function is to minimize y minus hx. So this is the objective function. So that is same as y minus hx y minus hx transpose y minus hx, that is equal to y transpose y minus y transpose hx minus x transpose h transpose y plus x transpose h transpose hx. That is equal to, so we can ultimately write it down like that, x transpose 1.
Sir, what about model questions,
Yeah,
sir?
yeah, sorry, yeah. So the model questions I tried to find out, but I couldn't find out. Sorry for that. But the questions in the final exam will be as similar. I mean, everything will come what whatever taught in the class, and those assignment questions also. So please solve those questions. And actually, this is my first time for that course TA session. So I couldn't find out. I asked and I searched, but I couldn't find out, and there was no response. Yeah, sorry for that.
Okay, sir, no problem. Okay. Thank you, sir.
H transpose H minus H transpose Y minus Y transpose H in Y transpose Y. So let us take another one vector. So let s is equal to small s is equal to x and 1. So and this matrix, let us take this matrix is same as L. Okay. So then this objective function will become, this thing will become S transpose L S. Okay. So the optimization problem now is kind of like that only. So optimization problem is transpose LS and subject to every entry in S, and that is the SI. SI will belong to, suppose it's a constellations is a QCOM constellations, or something like that. So let us take a QCOM constellation. So it will be in Q set, where I is from 1 to n. Okay. So what is this? Um, uh, So not n, let us take it's t. So 1 to t. So what is this q? Q is the set q constellations. Uh, or for the BPSK. So for BPSK, this q is plus minus 1. So for BPSK, this can be plus minus 1. So this is the optimization problem. Now, so for BPSK, psi belongs to plus minus 1. Okay. I less than equal to t. So then Si square is equal to 1 for all I. Okay, so uh, so this is the so this is the case. Then S and S transpose is equal to, there will be one matrix which will take one in diagonal elements, and all the off diagonal elements is there. So only the diagonal entries are zero, sorry, ones. So so now the optimization problem becomes minimizing S transpose ls or same as minimizing this S transpose, sorry, so this S transpose ls is equal to trace of S transpose ls, we can write down as this is a scalar. Okay, so then this will be same as, so trace of L S transpose. Okay, trace of ABC is equal to trace of BCA if the uh, dimensions matches for the if dimensions match for the matrix multiplication, that we can write down. Okay, or trace of AB equals to trace of BA if the dimensions match. So then this is equal to trace of L is S transpose. This is equal to uh, trace of, let us take S L into S, where uh, this capital S is equal to, is a matrix that is equal to S is transpose. Let us take. Okay. So then, sorry. So then the equivalent problem minimizing trace of LS subject to diagonal of S. Okay. So this is equals to one vector, or diagonal of S is equal to one vector. So this is the vector sign. So now, and another constants are S is a positive semi-definite. S is equals to, S is greater than equal to 0, and another one is that S is equal to S transpose. But this is the non-convex rank one of, this is the non-convex rank one constant constant. So to get the SDP, so we can do so. Uh, so relaxed for SDP. Okay, so this constant we can relax. So then for ML MIMO decoder, the optimization problem is that uh, minimize trace of ls subject to diagonal of s is equal to 1 vector, and as is greater than equal to 0, or as is a positive semi-definite. So using the eigenvalue decomposition, we can do using s can be written as s equals to q lambda q transpose. Okay, so this, here q is a matrix. So this is equals to, so this is the diagonal matrix containing eigenvalues of s in diagonal entries. Okay, so then this can be so this can be written as I is equal to 1 to n plus 1 lambda I qy transpose. Okay, so now, so as s is greater than equal to 0, so this lambda is also greater than equal to 0. So that is the definition according to the definition of the positive semi-definite matrix. So then and let us arrange. So then without loss of generality, we can write down, uh, we can take let lambda 1 is greater than equal to lambda 2 greater than equal to lambda 3. So all are arranged. Let us take. So then s can be approximated as lambda 1 into q1. Okay, where lambda 1 is the q1 transpose. So where lambda 1 is the largest eigenvalue, principal eigenvalue, largest eigenvalue of s, and q1 is the q1 is the eigenvector corresponding to lambda 1. So then so this is the approximation. So base rank 1 approximation. So this is the based on approximation. So now if this so s is found out, then we can write down s is equal to root over lambda 1, or as the lambda 1 is greater than 0, so we can write down root over lambda 1 q1 power half into root over lambda 1 q1 power half trans. Okay, so this is then will be s, and this is will be s transpose. So s is equal to root over lambda 1, sorry, s is equal to x, and 1 is equal to root over lambda 1 q1 q1 power half. So then from this we can from this we can estimate x set. Okay, so this is how we can solve or we can find out x set from the HTTP problem using the HTTP problem for the case of MIMO email detection. Okay, now I will take three questions. So short questions only. So now some assignment questions type questions. So here the first question is so the first question is a semi-definite program has the form the minimize norm of sorry norm norm of a subject to AI transpose X plus BI is equal to 0 and CJ transpose X plus DJ is equal to 0 and B option is minimize X transpose AX subject to X transpose EX is less than equal to 1. Option C is minimize C transpose X subject to summation of xi fi is equal to 0 less than equal to 0 and ax equal to b. Option D minimize C transpose X plus D subject to X plus B is equal to X transpose X plus sorry U transpose X plus B. So out of this you can see the definition of so the HDB problem. So this was the problem. So you can see that option C is obvious. Option C is correct. What is the option C? So this same as this problem. This yeah same problem. So this is the option C is correct. Now for the second question, the optimization problem with AX minus this can be formulated as option A second order cone second order cone option B quadratic option C linear program semi-definite program. So you can see the option C is curvilinear program. We can write it down. I think this is same. This is already shown in the class lecture also. So another problem, minimization problem. Minimize summation of xi. I equals to 1. I goes from 1 to m subject to C transpose X is equal to D, less than equal to D. Sorry, less than equal to D. So it's is a option A, linear problem. Option B, quadratic. Option C, semi-definite. Option D, second order cone. So answer is it's a linear problem because it's a linear equation, linear objective function. That's why. So that's all for today. So I can revise again, and if you have any question, you can ask me also. So first, for the optimization problem. So
Sir, can you explain linear program, quadratic program with example?
quadratic, na? Yeah, quadratic problem is that it's a quadratic means some for the scalar case some x square should be there, but for the vector case it will be some x transpose. So x transpose cx. Suppose this is the uh, yeah. So this is the scale. This itself a scalar quantity, but this is the suppose minimize this thing x transpose cx subject to some constant. So this is the quadratic problem because here suppose let's take x as a scalar, so it will be cx square. So that will be a x square term. So this is the quadratic problem. So this is the quadratic problem. But when only x is there, so like some c transpose x, then it's a linear program problem.
Okay, sir.
Okay.
What about SDP, semi-definite program, sir?
Semi-definite program, here we give an example, right? So the semi-definite program, the objective function can be anything. That can be linear. So the object function is linear. So for the semi-definite program problem, you just see the constants. So here in the constant you see this some matrix should be positive semi-definite, so it's a name hidden in the program also. So it's a semi-definite program. So in the constant if you see that some matrix should be positive semi-definite, then it can be a positive semi-definite problem. Here you see some linear combinations of linear weighted combination of matrices. The matrices are fi. So this fi, summation of xi fi is greater than equal to 0. So then that means this matrix will be positive semi-definite. So then in this case the optimization problem will be the positive semi-definite optimization problem. What semi-definite optimization problem, HDP.
Okay, sir. Sir, please explain first problem, sir.
Yeah,
Problem.
sure. So the first problem means this question one, or this thing semi-definite program details. Which one? First problem is this question. A semi-definite program has the form this question.
Yes, sir.
Okay, so a semi-definite program has the form. Which one is correct? Okay, A, B, C, D are options. So in the first option, minimize norm of A subject to some constant. Okay, but here you see there is nothing inequality constant. So positive semi-definite means here one inequality constant should be there, right? This one is an inequality constant. So that is not there in the option A. So option A should not be correct. Then in option B, it's x transpose cx is less than equal to 1. But here some matrix should be greater or less than equal to 0. But here it's just a scalar and that is less than equal to 1. So it can't be positive semi-definite constant. So then here, so this is matching. This is matching with our first SDB problem. So then this is the correct answer. So in the fourth case also you see this is also just a scalar. Okay, so this is also not matching, and there is no matrix involved here. So that's why option C is correct.
Okay, sir. Sir, how to find non-zero signal coefficients in this pass? How to find non-zero
Non-zero
signal?
signal coefficients
Please
for the
explain.
compressed sensing, right, program. Yeah, so that I can explain also. So that is there. I solved in the this class 2 days ago. So so you're saying about this type of questions, right? Consider the sparse signal estimation problem. This question.
Yes, sir. Yes, sir. I couldn't attend the
Okay.
last class, so please explain.
Okay. So the consider the sparse signal estimation problem. So this is the sorry. This is the system model itself. Okay. So this phi is the your measurement matrix, or what it's dictionary matrix or anything you can say. Just phi is the matrix, and y is the observation vector, and x is the sparse signal. So we need to find out x, but we know phi and y. So y is 143. This one is y, and phi is also known. This is a matrix. 0 0 1 0 0 0. So this is a matrix. So this phi and y both are known, but we need to find out x. How to find out? So the normal process, the actual process is just minimizing the L0 norm, L0 norm of x, and but that is not solvable actually. That is the that will take huge complexity. You can't solve it. That is a non-convex optimization problem. So then we can solve it by using the one greedy algorithm. One just in 2 3 steps you can solve it. So you need to find out you can solve it. So that one way is that orthogonal matching pursuit algorithm. So that only that way, sir, professor has told in the has mentioned in the class. So that OMP, there are other ways also, basis pursuit algorithm and many other ways. But this orthogonal matching pursuit is the very less complexity, and it's very easy to compute. So we will follow the we will find out the sparse signal using the orthogonal matching pursuit algorithm. So for the orthogonal matching pursuit algorithm, first of all, we need to take y. So y as a residue itself. Residue means some residue is a one vector. So at the beginning, we will set residue r is equal to y. Then we will find out lambda is that is another vector. Lambda is equal to r transpose phi, and we will take absolute of that vector. Okay, so that means r transpose phi means now r is y. So y transpose means 143 into phi. Phi is this matrix. So I will calculate that r transpose phi here. Then I will get r transpose phi vector. So this is the vector 445 373. So this vector 445 373. So then out of the entries, all the entries of lambda, I will see which is the maximum entry. So here you see this 7 is the maximum entry. Okay. Then I will check the what is the position of the maximum entry. So here the position is fifth position. It's occurring at the fifth position. So then I will take one another set that will contain only those positions. So here S is equals to 5 now, because fifth position it's giving the maximum value. Then so already I find out the position, fifth position. Then I will take the column of the fifth column of the matrix 5. Okay, so 5 was this matrix. This was the 5 matrix. The fifth column was first, second, third, fourth, fifth. So 0 1 1. So this is the fifth column. So I will take that column, and that column I will take, and I will set another matrix or vector, you can say anything. So this A is equal to only that column only, 0 1 1. Okay, now I will find out x by using this A dagger into y. A dagger means pseudo inverse of A into y. So what is the pseudo inverse? Pseudo inverse formula is there, right? A transpose A inverse A transpose, this is the pseudo inverse formula. So I'll use the pseudo inverse formula, then I'll find out x here. So that I have used it. So A transpose A means 0 1 1. Transpose means this is the row vector, then 0 1 1 column vector, then inverse of this multiplied with A transpose, then y. So this is just formula. So then that is giving 7 by 2. Okay, so this is the x. So it's only one scalar only. It's giving the scalar. So for this case, it's just a scalar. So there is no vector. Okay, so then I found out the one entry 7 by 2. Now residue I will find out. Again I will take again I'll find out the residue that now it will give. Earlier it was y, so now it is y minus ax. Okay, so where y is equal to 143 and a is a vector 0 1 1 and x is 7 by 2 we are getting now. So then I'll subtract y from sorry I will uh, I'll subtract this portion ax from y. Okay, so that is giving one half minus half. This is ultimately residue we are getting. Now I'll follow the same procedure. This is the same procedure I will follow. Then I will find out second value of s. Okay, then I will find out the second value of s. So let's do that. So now I will calculate the lambda. Lambda is equal to R transpose phi. Then absolute of that R transpose phi. So that means it's giving 0.5, 0.5, 1.5, 0.5, 0.5, 0, and 0.5. Now I'll check the maximum position of the lambda. So its maximum position is this third position is giving maximum 1.5. So then S will take third also. Earlier it was fifth. Earlier it was fifth. Now it's giving third position also. So now S is a vector which will contain third and fifth, which will contain two elements, 3 and 5. Now I'll find out A. A is another matrix that will take only those columns of 5. So here third and fifth. So it is taking third column and fifth column of 5. So third column is this is the third column 110 and fifth column is 011. So that is taking itself 110 and 011. So then I'll find out x again here. X is equal to a dagger y. A dagger means A transpose A inverse A transpose y. So A is this matrix. This is the A matrix. Then A transpose A into A transpose y. So that I am calculating. Uh, so yeah, I'm calculating here. So then after few steps, I am getting x is equal to 1 3. This is a vector. So then I'll find out residue again. So this process will be going on until we get some convergence. Okay, so let us check convergence. Okay, so then I'll find out residue again. Residue equal to y minus ax. So y is equal to 143 and a is this matrix now. So this matrix into x is this 1 3 1 3. Okay, then if you put that all the values here, and then you will get residue equal to 0. So now the residue is 0. So it converged already. It converged. It is converged or it converges. So now no need to go to next step. It already converges. But if it is not 0 in this case, then I'll go in third step also till we are getting some convergence value. Not only 0, we can get some 10 power minus 2, 10 power minus 3 convergence also. So that is also fine. But this is a process. So here only here after two steps, it's giving convergence. So it's getting convergence. So we don't need to go next step. Okay. So the ultimately the solution is so it is converged. Now the positions are sorry. Now the positions are 3 and 5. 3 and 5 at last the positions are 3 and 5 and the values are 1 and 3. Okay, 1 and 3 values x equal to 1 and 3. Now put 1 and 3 values in those positions. Okay, so the x is a sparse vector. X is a sparse vector, so all will be zeros except this third and fifth position, and the values will be 1 and 3. These 1 and 3 values, and all others will be zeros. So that is the sparse signal estimate of x. Okay, so now you can, yeah, this is the process. Did you get it?
Yes, sir. It's a lengthy process.
Yeah.
Mm. Sir, you have uploaded lecture notes in this. All the slides are in a single page. So you didn't.
Yes.
Yes, sir. After taking printout.
Yeah, actually that happens. So uh, yeah, that is one problem. So I don't know how to solve that problem. That yeah, after taking printout, you will get only one single A4 sheet, and my
Yes, sir.
letters will be very small. You can't read it. That I observed.
Yes, sir.
That I
Yes, sir.
know. For our case also, when teachers taught us, that same thing happened to us also. So yeah, I don't know. That's a one problem in this writing iPad. or tablet, but I don't know how to solve it. One solution is that there is a very so that one process you can do is that you can
Yes,
open that
screenshot.
file in
Yeah.
the Adobe Reader or something, Adobe Acrobat. Then you can take some screenshot of some portion. So it will be some 2 3 portions of a page. Okay, and take those printers and save another image or another PDF. Then print those PDFs. That is a very lengthy process. You don't need to follow. So just see in the PDF itself. I don't know, yeah, how to solve that problem.
Okay, sir. Sir, can you solve assignment 11 problem, sir, now?
Assignment 11 problem, due date is over or no? It's still
Over, sir. Submitted. Over, sir.
over.
But, yes, sir.
Okay, okay. Actually, I need to then open that problem set. Yeah, 1 second. Oh, it will take time. So, you tell me the first question, or whichever you want. You can tell me the question, then I can match. So please tell.
The optimal solution X to the least norm optimization problem below is minimize X subject to Y is equal to AX.
Okay, okay, 1 second. No, no, 1 minute. Then I have to open the assignment question, please.
Okay. Okay, sir. Sir, please check chat box.
Okay. List norm optimization problem below is y equal to correct. You know, okay. Subject to optimal solution.
We have to solve or the answer is standalone.
Yeah, 1 minute. So I'm opening it here. Assignment 11. Yeah, the optimal solution extra to the least norm optimization problem below is. Yes, correct. So it's oh, this question is already solved in the class, right? That time I solved. This professor has solved this week uh, lecture 10 9. Lecture 9 maybe this uh, something optimization problem X subject to graph algorithm problem. Then lecture 8. So 8. So in the SAR's professor's lecture, maybe not here, maybe I forgot. Here also I remember these things already solved. Okay, so in the lecture series here, so this is very straightforward. This lecture series here solved, right? This A transpose inverse Y. So this itself is a solution of least square problem. This is a pseudo inverse of A into Y. So that is there, right?
The
So we
answer is the
can.
standard one. No need to solve it. Yes, sir.
Yeah, standalone. So no need to solve it. So the solution is A transpose inverse into Y. So that's what only.
Sir, can you solve assignment
Yeah,
11?
sure.
Fourth
Then
problem. Fourth problem in assignment 11.
fourth
Actually, A
problem.
is given.
The
Question is
maximum value of X transpose AX for
A.
X less than equal to 1 is this thing. Okay. So
Yes.
this is the maximum value of X transpose AX.
A is given.
So yeah, A is given. So
But
correct.
what about
So
A?
correct. So the solution is like that only. I think this question also I've solved, but still I can solve it. So let's open latest lecture was 12. So the solution is like this only. So 100. So this is the question 4 is that A is equal to 4 1 2 1 sorry 1 2 plus 2 2 minus 1 2 minus 1. So did you calculate this whole things? Did you multiply? So 4 into 1 2 into 1 2 means okay. So no need to do those things. So let us write it down like in this way actually. Okay. So this is one. So the rank of this matrix, rank of this is the rank is equal to 1. This is also rank 1. Okay. So this is the rank 1, rank 1. X transpose A, optimal value X transpose AX. So is the lambda. Lambda is the eigenvalue. Eigenvalue is not sphere. What is the eigenvalue? Okay, correct. Then no need to do these things. So then find out the calculate the whole thing here. So 4 into 1 2 1 2. So 1 and 2 2 4 plus 2 4 minus 2 minus 2 1. So then 4 is equal to 4 plus 8 12. 8 plus 8 minus 4 4 itself 8 minus 4 4. 16 plus 2, 18. That's it. Yes, correct. So now find out the eigenvalues of A. Eigenvalues of A. Okay. So A is this thing. So then A minus lambda I determinant is equal to 0. So that means A is this 12, 4, 4, 18. So 12, so 12 minus lambda, 18 minus lambda, then 4 and 4. So 4 and 4. Determinant of this equal to 0. So that means 12 minus lambda into 18 minus lambda minus 16 is equal to 0. So uh, so that is equal to 12 into 18, 12 into 18 minus 12 lambda minus 18 lambda plus lambda square minus 16 is equal to 0. So this is the 30. So 30 lambda. So lambda square minus 30 lambda plus 12 into 18 minus 16 0. So can you calculate the value? So 1 minute. So, 12 into 18, 12 into 18 minus 16 is 200. So lambda square minus 30 lambda plus 200 is equal to 0. So it's we can write down lambda square minus 20 lambda minus 10 lambda plus 200. Lambda minus 20 and lambda minus 10. So lambda equals to 20 and 10. Okay. So these are the eigenvalues. Now the question was the maximum of this, maximum of X transpose X. Okay. So that is equal to, so maximum X transpose X. So if you solve that thing actually, so it will be uh, one second. So there is one theorem is also there, Rayleigh theorem. So that says that this X transpose X divided by X transpose X is less than equal to, is less than equal to and greater than equal to. So this is lambda max, maximum eigenvalue, lambda mean minimum eigenvalue. Okay, where A is a symmetric matrix, where here also A is a symmetric matrix, symmetric matrix. So this is a Rayleigh solution problem. So anyway, you can solve that thing actually, maximum of X transpose X. So you can solve this thing. The process is same. Max of X transpose X means just derive, so minimum of minus of X transpose X and subject to X transpose X, X transpose X is equal to 1. So you can solve that thing. So there ultimately we will get the solution like that, Ax equal to lambda x. Then if we put here, then you will get x is equal to maximum lambda max. That is the maximum eigenvalue. So that means here the maximum eigenvalue is 20. To solve the solution is 20. So this question is already solved maybe for the MIMO channel case. If you see, the maximum eigenvalue will be the answer. So that is like that only. So the ultimate thing is that you need to find out the eigenvalues of A and then see that what is the maximum eigenvalue A of A. So if the question is maximum, if the question is minimum of X transpose X, then the solution will be minimum eigenvalue. Thus 10, 10 will be the solution.
Okay, sir. Can you solve the 10th
Okay.
problem, sir, in the assignment 11? 10th problem.
Yeah, that's all for today. So actually, I will have one more last class. I'll just revise the topics from the first to 12 weeks. For 12th week. So that will be on Tuesday or Wednesday. I forgot some day. So morning maybe some, okay, so few minutes only. So that will be sent to you maybe in through mail. So that in that class I'll just solve the not solve, I'll just go through once the summary. So you can ask me also there, or here also you can ask me. So, or if you find out any difficulty in solving any question or assignment question, so you can mail me. Okay, so my mail ID is already shared. So, do you know my mail ID, or shall I write down here in the chat section?
Please tell now, sir. I didn't note.
Okay, my mail ID is niladrih@iisc.ac.in. niladrih@isc.ac.in. So you can mail me anytime. So I will be available anytime. You can mail me. So I will try to send or get back to you as soon as possible. Okay. Yeah, that's all. So thank you. Have a good rest of the
Sir,
weekend.
NILADRAH.
Yes. Can
NILADRAH at iiscac.in.
yeah,
Is it correct?
NILADRIH.
Okay, sir. Thank you,
Yeah,
sir.
correct. In the chat section also I have written, so you can see that. Okay.
Okay, sir.
Yeah.
Okay, thank you, sir. Can you
Welcome.
solve 10th problem in assignment 11, sir?
10th problem. Okay. So the classification error is given as consider sets of points xi and yi regularly classified that maximize the distance separation while also minimizing the classification error. Uh, okay, okay. So this is maybe from the last lecture or the classification error. So I need to go through there. Okay, so that will be maybe in the last class that is solved. I don't know. 1 second. So uh, seems to be from there itself. So classification error regularized classified that maximize the distance of separation while minimizing the classification error. Yeah, I need to go through it 1 second. I will tell you, or okay, later in the next class. Sorry for that. Yeah, yeah,
Sir,
I understood your
this is the
question.
last class or one more class is there?
Yeah, only one more class. That will be the last class.
Okay, sir.
Okay, thank you.
Okay, thank you, sir.
Actually, today there is one program in this campus. Maybe you are hearing the noise also. That's why. Yeah,
Okay, sir.
yeah. Sorry.
Okay,
Thank
thank
you.
you, sir.